Today I'm going to continue about the notion of a p-adic Frobenius structure. But before that, let me recall you some notions that we have seen yesterday. And for that, I'm going to start with the following set introduced by Julian. So we have the set A is the set of algebraic power series. Okay. Here is T. And also we have the set D, is the set of the definite power series with coefficients in Q. So one of the problems that Julian told us is the following one. When does F belong to D minus A? Okay. So of course this set is not empty. There are power series which are definite but not algebraic. So how to determine that a power series is definite but not algebraic? Okay. So there are three methods. At least there are three methods to study this question. The first method is analytic, that is maybe done by Flageolet. The second method is using the theory of the Galois differential theory. And the third method is based on from point of view of algebra of the reduction modulo P. So in this lecture, we are going to focus in the third one, in the reduction modulo P. Okay? So let me illustrate this point of view of the reduction modulo P with the following example. So I think, yes, yesterday we have seen this example. So we take R, an integer bigger than 0, and we consider the following power series. The coefficients are the binomial to n power R. Okay, so of course this power series belongs to this ring. Okay, and for example, in the case R equals 2, it turns out that FR 1 over yes, I think is the hypergeometric series introduced by Duco, 1.5, 1.5, 1T. So actually these power series are hypergeometric series, but in the particular case of R equals 2, we have this hypergeometric series, which we have seen yesterday is important in several areas of mathematics, even in physics. Okay, so but it turns out that for R bigger than 1, this power series is transcendental. But we can prove that using the reduction modulo P or the tool of algebraicity modulo P. So the first observation is the following one, or maybe a fact. A fact, but maybe we are going to use, of course, P is a prime number, so the reduction of R modulo P, FR modulo P, is the power series obtained by reduction is coefficient modulo P. Or we can reduce it because the coefficients are natural numbers. And it's a power series with coefficients in SP. Okay, so that is the first observation. The second one, and this is important, is the following one. Yes. So actually, in the first exercise is proposed by Julian Roch, we are going to see that this power series is algebraic over SPT. Okay, so that is not, actually that is not easy to prove it, but we are going to see that in these exercises. Actually, we can do better, and because FR is solution of this polynomial, yes, I think it's this one. Okay. So in the exercises, we are going to prove actually this power series is a solution of this polynomial. So that is good. But even more in these exercises, we are going to see that using the fact that the reduction of modulo p of this power series is solution of this polynomial, we can prove it that FR is transcendental over, of course, over Qt. But it's important to know that R should be bigger than 1 in this approach. So this approach actually is approach used by Chafariz and Woodcock. So in these exercises, actually, we are going to prove we are going to see the method used by Chafariz and Woodcock. Yes. So that is the first fact. So the fact one. Okay. Yes. Yes. Thank you. Fact two. We can prove that if R are bigger than 1 is transcendental. Now here we can reuse it for R bigger than 0, but because in the case R equals 1, FR is algebraic. But for R bigger than 1, the FR is transcendental. Okay? So that is important to know. Yes, it is actually this polynomial. Yes, it's transcendental over Qt by using. Okay, that is the approach given by Chafariz and Woodcock. Okay, that is finished. Maybe I won in the year, but I think it's more or less the year. So, and according to me, that is the first time I see in the literature where the reduction modulo p is used in order to get transcendental results. Okay, so that is nice, but there is another important fact here is that this power series FR is a solution of a hypergeometry operator. Okay. Of okay. And here delta is, maybe I'm going to use the two connotations delta. Okay. So, but it turns out that also we learned from Marshall's lecture that this operator has Frobenius structure. I'm going to recall the definition in a few minutes for almost prime numbers. Okay. So, but somehow we have to use. We are going to see that we can use the fact that Fr is solution of this hypergeometry operator, which has Frobenius structure for almost prime number P, in order to prove that actually Fr, the reduction modulo P of Fr, is algebraic over Fpt. Okay? So that is the main point, at least of this, for today, to prove that somehow when you have Frobenius structure, you get algebraicity modulo P. So, R as p-adic Frobenius structure or P bigger than 2. Okay. So now that is at least the motivation. We have this power series. Can we reduce in modulo P? The reduction is algebraic, but also this power series is solution of a differential operator having a strong Frobenius structure. And the idea is to show that the Frobenius structure actually implies the algebraicity modulo P. So let me recall the definition of from the Frobenius structure. So we take a matrix with coefficient in Qt. We say that the system has p-adic Frobenius structure of period h if there is h in an EP so that we have the following equality: take h minus p to h z maybe t minus 1. Okay, that is the definition. This notion was introduced by Dwork. This notion, okay, yes, maybe. Because for me, actually, this is the Frobenius structure is a Frobenius action over the solution of this differential system. Actually, that is the main point. Maybe that is a good remark. Yes, maybe that's it. I don't know. I don't remember if this remark is in the exercises, but the system has p-adic Frobenius structure if only if there is, let's say, operator B is where the BE or BI, I'm sorry, is an analytic element, belongs to EP. And for every solution Y. Okay, maybe here I see in this remark, I see A as a companion matrix of a differential operator, okay? For every solution Y of the composition of B YT to PAs is solution of the differential system. Okay? So that this remark gives more that is a Frobenius action over the solution of the differential system. Okay? Okay, yes. Yes, but here A is a companion matrix. Yes, but what? Yes, I agree. But here, Y is, I mean, solution of this differential system. Actually, Y is the solution of the differential. Yeah, the first component. Yes, let's say yes. Yes. Okay. So now, and also at the end of the last lecture, we learned the following theorem. Yes, I think, yes. Yes. H and actually this B, to construct this B is the first row of H. And to get H actually is you take the B, this BI, and you take the derivative. That is the, okay? Sorry? Okay. Yes, that is Masha told yesterday. Actually, this H means that these two systems, A and the given by this matrix, are equivalent. Okay? So yesterday at the end, Masha stated the following theorem. We take L a differential operator. Okay? And suppose that L is components of L are in Q, and the third one condition is the monodromy of L is rigid. Okay? Not so much, actually. I'm sorry?
In the problem sheet.
Yes, in the problem. Yes. Then L has, yes, then there is an integer h bigger than 0, so that L has a p-adic Benz structure of period h for almost all primes p. Okay, so and also Masha described the set of such numbers, prime numbers. So I'm not going to do that. But the main point of this theorem is actually we can apply this theorem to hypergeometric series. Why? Because, okay, but we have to be careful because we have to take the parameters as a rational numbers. So that is the main point of this theorem. So maybe it's a corollary of this theorem. We take alpha, a vector which entries are rational numbers which are non-negative integers, and we consider another vector beta which entries are rational numbers which are not negative integers. So we have okay, suppose that alpha I minus beta I is not an integer, every I and j. Okay, so with these assumptions, actually the hypergeometric operator with parameters alpha beta is defined like this. We take beta n as 1, okay? Maybe here is 1. Okay, so with this assumption here, okay, it's well known that the hypergeometric operator is function. As the alpha betas are rational numbers, the exponents are rational numbers, and the fact the monodromy group is rigid is known from Level. Level has proven that the monodromy group of this hypergeometry of the hypergeometric operator with this assumption, for this reason, this assumption is very important, implies that the monodromy of L is rigid. So we can apply this theorem. Then p-adic. Almost all primes. Okay, in the exercises we asked for to find out the set of prime numbers for which the hypergeometric operator has a strong Frobenius structure, and also we asked find out the period. Okay. So for this, yes. Yes, but I don't. Maybe no. Maybe not false, but it's true. The argument used in the theory doesn't work because we use. Yes, I think it's true because in general the hypergeometry operator are factors of Picard-Fuchs, so it should be true. Okay, I think. Yeah, the problem is when you assume that is, of course, that find out the good primes and the period, but I think it's true in, even with this conclusion. Yes, that. Yes, yes, because for the when the primes appears in the denominators, the radius of convergence is less than 1. That is not good. So Masha explained yesterday that when you have Frobenius structure, the radius of convergence is at least 1. So for this reason, we exclude this prime. Yes. When you have two systems which are equivalent, and one of them has Frobenius structure, the other one has also Frobenius structure. That is because it's actually the Frobenius structure is equivalent to between two matrices, between two systems. Okay. So now here we note. Okay, I say that FR is solution of this hypergeometry operator. Here, all the betas are 1, and alphas, all the alphas are 1.5. So we can apply this theorem. And for this theorem, we know that this hypergeometry operator HR has Frobenius structure for almost prime number P. Even more, as we know the set of prime numbers which this hypergeometry operator has Frobenius structure. In this case, in this particular case, we know that this operator has Frobenius structure for all prime numbers P bigger than 2, because it's the only P that appears in the denominator of alphas. Okay? And also the period in this case, for this particular case, is 1. Okay, so, but at the beginning I told you that the idea is to see that the Frobenius structure somehow implies the algebraicity modulo P. So I am going to recall the definition of algebraicity modulo P. What does that mean? So we have the following ring, ZP. Okay, of course, P is a prime number. So this ring is the ring of rational numbers, so that A, B are coprime, and P, D are also coprime. In fact, we can reduce it, the elements of this ring modulo P, and the residual field is Fp. Okay. Now for a power series, Ft with coefficients in this ring, in Zp, then we can reduce it modulo P, I'm sorry, and the reduction is just the power series obtained by reducing each coefficient modulo P. And this power series belongs to Fpt. Okay, that is the reduction of F modulo P. That is something here. So here is the definition of algebraicity modulo P. So we take a power series with coefficient in Q. So we say that F is algebraic modulo P if, first of all, we can reduce it F modulo P. That means the coefficient of F belongs to ZP. Okay, and the reduction of F modulo P is algebraic over FPT. So as an example, FR for all R is algebraic modulo P for all price numbers P. Okay? Of course, it's not obvious when you can reduce it a power series F modulo P. In this case, we can do it for all prime number P because FR, yes, here, the coefficients are integer. Okay? Yes. No, here, AB. Yeah, yes, exactly, yes. Here? Yeah, no, that means it's algebraic in the usual way. It's the solution of a polynomial with coefficient in FPT. Yes. Any? Ah, no. It's any. You mean something as here? As this polynomial P? No, here I don't care about the polynomial. I only ask that is algebraic. Okay? Okay, so we have the following theorem. Ah, okay, yes, there is something important to say here. Okay, if we have a power series with coefficients in Q, algebraic modulo P, then the algebraicity degree of F modulo P is just the degree of the real extension of FPT when you add F modulo P. For example, in this case of FR, since FR is solution of this polynomial P, you can say that the algebraicity degree is at least P minus 1, okay? Because actually that equals to the degree of the minimal polynomial of the reduction of F modulo P. Okay? So we have the following theorem. We take a differential operator with coefficient in Qt. Of order n, and F power series with coefficient in Q, solution of F. Okay. So if you can reduce F modulo P and L has a p-adic Frobenius structure of period H, then F is algebraic modulo P, and the algebraicity degree of F modulo P is bounded by P to n squares times H. Okay, so this theorem shows the connection between that actually the Frobenius structure implies the algebraicity modulo P. Okay. For example, in the particular case of Fr, you can apply this theorem, but you don't get actually that, because if you apply this theorem for Fr, so the period, we know that Fr is solution of the hypergeometry operator. The period is always 1. So here you have 1, and here you have the order is R squared. So that is only that you can say it, but actually this shows that you can even do better than this theorem in some cases, okay? For the degree, for the algebraicity degree. Yes? Yes, that's that. Yes. Mm-hmm. Yes, somehow that is the idea. To prove this theorem, you use this operator B. But it's not only to reduce this operator. There is more thing, because the idea you are going to see that using this operator, you can see F modulo P inside an vector space, and this vector space is closed by twisting the Frobenius H times. So somehow you are going, sometimes at some point you are going to finish, and you get that the reduction of F modulo P should be algebraic. But it's not only to reduce this operator B modulo P, okay? But you use it in the proof. Okay? Yes. 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 Of course. Yes. p-adic one. Yes. But from this relation over EP, actually this relation is over EP. You can show that actually you can reduce this relation modulo P, and you get the theorem. Okay, is that? Yes, actually you get a relation. You show that F is algebraic over EP, but also you can show that this relation you can also reduce in modulo P, and you get the theorem. That is the main point. But this relation is obtained using B. Okay? Okay, now it's here. So now, so as I told you, we use in the example of FR, we use the algebraicity modulo P to show that FR is transcendental over Qt. So now the idea is, of course, try to use the algebraicity modulo P to get a transcendental result. And why that is interesting? Because actually it's because it turns out that when you have a differential operator having a strong Frobenius structure, the holomorphic solution is a G function. And the G functions are very special power series, let's say, and they are very important in many in some areas of mathematics, as geometry or combinatorics, and even for transcendental results. But there are so I'm going to introduce the following set. So we have algebraicity modulo P. That is the power series with coefficients in Q. So that exists as an infinite set of prime numbers. So that for every P in S, F is algebraic modulo P. Okay? And also we have the set Frobenius structure, and of course is the set of power series with coefficients in Q. So that F is solution differential operator having p-adic Frobenius structure for almost all prime number P. Okay, and also you have this set Frobenius structure star, set of power series with coefficients in Q, so that F belongs to Fs, and you can reduce it F modulo P for infinite many prime numbers, and exists as infinite set prime numbers. So that for every P in S, F belongs to ZP. Okay? Why I introducing this set? Because we have the following diagram. Of course, Frobenius structure, maybe, yes, Frobenius structure, inside of Frobenius structure, and thanks to this theorem, Frobenius structure is inside of a star is inside of algebraicity modulo P. Okay? Here, no, the period is not important here. Only the solution of a differential operator having a strong Frobenius structure for almost all P. The period is not important here, okay? Maybe, yes, maybe, but the important thing is that even if the period is different for every prime number, it's at least algebraic. That is the important thing here, okay? So there is a set that I'm not introduced yet, but I'm going to do it in a few minutes. But for the moment, I am going to write down is the set of G functions. Okay? So what is the importance of actually of the set of G functions? Is the set of Frobenius structure is inside of G functions. Okay? There is a famous conjecture in this context, is that the conjecture of Bombieri-York, and this conjecture in fact implies that probably G functions are inside of Frobenius structure. That is a conjecture, okay? Now, but actually there is a recent conjecture due to Adamczewski and Delegge, and this conjecture somehow implies that G functions are inside of algebraicity modulo P. Okay, that is there is a lot of rows here, but let me tell you that G functions, yes, that is a conjecture of Adamczewski. Delegge. That I am going to state in a few minutes. So that is also a conjecture. But even if the G functions are inside Frobenius structure is a conjecture, there are two big examples of G functions that we know this conjecture is true. So, for example, we know the diagonals and hypergeometry series. Maybe I am going to write down here diagonals, which I am going to define in a few minutes. But that is the motivation, the hypergeometry series n(f(n)-1) with rational parameters. So for diagonals, we know that are G functions. Hypergeometry series are also G functions. We know that when you can reduce it, even if you cannot reduce it, hypergeometry series are inside Frobenius structure. As also diagonals are inside Frobenius structure. That is a result due to Cristol. Okay? And also we know that the Adamczewski-Delegge conjecture is true for diagonals and hypergeometry series. Okay? Maybe I'm going to use another color for conjectures. Yes? Yes? Yes, yes. Yes, the only difference between Fs and Fs star is that in Fs star you can reduce it F for an infinite set of prime numbers. No, not necessarily. It exceeds. Yes, thanks to theorem, as I state here. Yes, because I say that F belongs to Fs. F belongs to S. Yeah, yes. Yes. Okay. Yes, 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 of course. I'm going to define the functions and diagonals. We know hypergeometry series. Yes, I'm going. Our Frobenius, our solution of the operator having Frobenius structure for almost prime number P. Okay. So, but the idea of this diagram, of course, is to show that actually algebraicity modulo P is something important in the inside of G functions. It's not something lives alone. It's inside of this area. And the idea is, of course, to use the algebraicity modulo P to study the transcendental algebraic independence of G functions. Ah, yes, 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 yes. Thank you. Yes. Is the okay, so here is the definition of G functions. So here is the definition of G functions. So this class of was introduced by Siegel. So sorry, that is 29. So we say that F a power series with coefficients in Q G function. First of all, G function if there is a non-zero differential operator L with coefficient in Qt, so that F is solution of L. Okay, that is the case, for example, for hypergeometry series. The second one is that there is a constant C bigger than 0, so that the absolute value of An is less than C power 2 n plus 1 for all n. Okay? And the third condition that exists another constant D bigger than 0 and a sequence Dm, that is an integer sequence. A sequence of integers Dm bigger than 0 so that dm times an is an integer for all n less than or equal to m. That is the definition. For example, in the case of okay, yes, yes, thank you. With dm less than d power to m plus 1 and thank you. So here is some example of G functions. So the first is given, of course, as I tell you, there is two big families of example given by diagonals and hypergeometric series. So I'm going to introduce the diagonals. So in this case, we are going to take yes, we have the polygon operator known as the diagonalization operator. N is an integer. So we know we have the ring of power series in n variables, which are algebraic over the field of rational functions in n variables. So this operator goes to the ring of power series. So you take power series so this operator just take the diagonal coefficients. It means B here is G. You take the coefficients which are on the diagonals, and that is all. In which context? Okay, that's I know is that he wanted to study actually this, as I know, this definition is inspired on the properties of the geometry series. That is the reason of G appears, because somehow the geometry series satisfies these two conditions. So he wanted to study in a more general context this kind of properties. That is the reason of the name of G. But the true reason I don't know what is he had in mind, but I don't know. Because he in the same paper he also introduced the E functions, and the E functions are inspiring in the exponential. So, but okay. And so here is the definition of a. Or maybe I don't know, but because at the time I don't know if the notion of come from geometry was already in the literature. So I don't know, because the come from geometry is maybe from York and Bombieri and Grothendieck. I don't know, but maybe G is also from geometry. I don't know, but okay, but yes, maybe yes, that is yes, maybe okay. So this I remember this ring is the ring of power series in variables which are algebraic over the rational field with n variables. So we say that f a power series is a diagonal of an algebraic power series. If there are an integer n bigger than 0 and f an algebraic power series in the ring, in this ring, so that f is equals to the diagonalization of f. Okay? So here is an example. For example, sorry, F2. I recall you the definition. F2 is this power series. This is a diagonal of an algebraic power series. Why? Because actually you can take this rational function 1 over 1 minus t, 1 minus that is equal to A1 to A4, the binomial of A1 plus A2, A3, A1, I'm sorry, times A3 plus A4, A3. Okay? And of course, this rational function is an algebraic because it's a rational function, and the diagonal is easy to see that is actually F2. Okay, so in this case, so here we have already know that F2 is a hypergeometric series and diagonal. Why? Why does this happen? Because here you take the A1, 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 does it give it that? Where no? Here? Okay, that is I think this is good, no? Maybe there is something missing. Okay. No, why? No, because actually this one, not this is good, but we can check an after. But I think this equality is true. This one. Okay, so here is another example. This example is important because here we have an example of the hypergeometric series which are a diagonal, and now we are going to give you an example of a diagonal which are not is not a hypergeometric series. So this example is the generating power series of apparent numbers. You have 80. That is the generating power series of apparent numbers. Okay, and this is a diagonal because actually this is the okay. Well, but that is the same thing, no? Yes, that is the product of 1 minus t, 1 minus t times the product of 1 minus t3.
It was called 1 minus t, 1 minus t2.
Okay. Okay, I don't. In this moment, I don't see it. What do you say? But okay, but here this A actually is the diagonal of these rational functions 1 minus t times 1 minus t1 times 1 minus t4 minus t0 1 plus t1 1 plus t. Okay, so that is only another example, and the main point of this example, 80 belongs to Diag. Of course, here Diag is for diagonals of an algebraic power series, but it's not a hypergeometry series. With rational parameters. Okay? Okay, yes. So here is another example. This is actually a result due to Fürstenberg. If f and that is the year. If f is algebraic, maybe algebraic over Qt, then f belongs to f is a diagonal of a rational function. Here, when I say rational function, it's a rational function that is in this ring. Diagonal of okay, so here is another interesting example. The algebraic power series are diagonals. Actually, yes. Actually, it's even better. F is for some F in, okay? So now, actually, that is another important theorem due to Fürstenberg and after, and also proven by the Lignan. This theorem says the following thing. Yes. So here is some proposition. This proposition is about some properties of diagonals. So if f belongs to the then f is an integral. That is, there is a constant c, a rational number, not zero, so that f times f c times t is a power series with integer coefficients. Okay? Okay, so even better, that's a consequence of this proposition. So if f belongs to F, then f is a power series with coefficient in ZP for almost all prime for almost all prime numbers. Okay? So in other words, if you have a diagonal, you can reduce it modulo p for almost prime numbers p. That is a good point. Another point is that is the result due to Deligne and Fürstenberg. And this result is important because connects something in this diagram. So Fürstenberg and Deligne. I don't remember. That is the year. Okay. So if f belongs to the F, then f is algebraic mod p for almost all p. Almost all prime numbers p. Okay? So in other words, if you have a diagonal, according to that, you can reduce it for almost all prime numbers p, and the reduction is algebraic over fpt. Okay? Here we have to be careful because actually Fürstenberg and Deligne proved the theorem for a field with characteristic p. But here you can reduce it. And the reduction is again an algebraic power series because the reduction is again a diagonal of an algebraic power series because you can reduce it this power series in the example. Okay? In the definition. So you can apply the theorem of Fürstenberg and Deligne. So somehow diagonals are inside this set. But using the crystal results we have for Benut's structure, we can apply this remark and the theorem as I showed in the first part of the lecture, and you will also get inside. So there is two ways to show that diagonals are inside of the set of algebraicity modulo p. Algebraicity modulo. Okay? So the Deligne raised the following question. We take f a diagonal. Okay. So it asks, since, before I say the question, according to this remark, we can reduce it f modulo p, and the reduction is algebraic over fpt. So the linear question is somehow is natural because he asks about the behavior of the algebraicity degree of f modulo p, how the algebraicity degree behavior with respect to p. And in this question, he proposed that the behavior is polynomial in p. Okay, so is there a constant p bigger than 0, so that the algebraicity degree of f modulo p is less than p to t for almost all p. Of course, this question makes sense because we can reduce it for almost all p. Okay. Yes. Yes, so the lineage shows that this question has a positive answer in the same paper when f is a diagonal at 2 diagonal. No, I'm sorry, 4 diagonal. Okay? And 10 years ago, Adamczewski and Bell shows that this question has a positive answer. Okay? So let me say that. Okay, if you remember the first example for FR, for this example, we can take C equals 1, because FR is solution of a polynomial of the algebra where with degree P minus 1. Okay, okay, so the an affirmative answer to this question. Okay, but the interesting point here is the following one, and that is the remarkable point, is in some cases the Deline's question makes sense even for these functions which are not diagonals. Because in some cases you have g functions that you can reduce it modulo p for infinitely many primes. So you can ask the same question: is there is a constant c so that the algebraicity degree is bounded by p to c for such that prime numbers? Okay, so that is something important. So for example, if you take the following hypergeometry series, HT, Still is not a diagonal because still is not an integral. Okay, that is the hypergeometry series 2f1 1 over 5, 1 over 5, 2 over. Okay. However, you can reduce this power series for an finite set of prime numbers. Okay. However, for P congruent to 1 modulo 35, HT belongs to CP. Okay? In other words, you can reduce HT modulo P for these prime numbers, and the algebraicity degree in this case, again, is less than P. So you have here an example of a G function which are not diagonal. However, you can reduce it for an infinite set of prime numbers, and from these prime numbers, the linear question has a positive answer. So the Adamczewski-Delay conjecture actually says that the linear question is true for any G function when you can reduce it modulo P for an infinite set of prime numbers. And actually, we have a lot of examples of G functions which are not diagonal, so that the conjecture, as I tell you, is true. So let me state the conjecture. Okay, so f a G function, let f be G function. S an infinite set of prime numbers so that for every P in S, you can reduce F modulo P. Okay. Yes. I'm going to say the conjecture. I stop. Okay. Then first of all, the reduction of F modulo P is algebraic. Of course, over FPT. For almost all P in S. And the second one, there is P bigger than 0, so that for all P in S, verifying the condition 1, the algebraicity degree of F modulo P is bounded by P to C. So as I told you, the conjecture is true for diagonals, thanks to the work of Adam Chesky-Bell, and also this conjecture is true for hypergeometric series. Why? Because we know that the hypergeometric series are solution of the hypergeometric operator, and the hypergeometric operator is equipped with Frobenius structure for almost prime number P, and also I state the theorem that when you have Frobenius structure and you can reduce it, it's algebraic modulo P, plus we can also give for the hypergeometric series, we also have this C explicitly, and this C doesn't depend on P. So we have all. This constant C? For the hypergeometric series, actually C equal to, is the order is n squared times phi d, where d is the least common multiple of the denominators of alpha psi and beta psi. D is so of course this C doesn't depend on P. So that's, I stop here. No. It's not sharp. Yes. Yes, I think there is some example when, of course, we can do better than that, than this concept. Yes, I don't know, yes.
Thank you very much.